Okay, our next presenter is Dan Bruder. I don't think that was intentional, but it's amusing me, so there we go. Dan is going to be presenting modeling and control of soft robots using the Koopman Operator and model predictive control.
Thank you. So modeling and controlling soft robots is difficult because they have infinite degrees of freedom and highly nonlinear dynamics. So our goal in this work was to develop a way to build models of soft robots that could be used with established model-based control techniques. To that end, we take a data-driven approach. First, because most physics-based models of soft robots tend to either be too simple to capture their dynamic behavior or too complex to be used for real-time control. And the second reason we use data is that soft robots, it's easy to collect data on them because you can safely give them random control inputs without risk of damage. Now, instead of learning a black box model from data, we thought to use the Koopman operator because it provides an explicit linear model that captures the global dynamic behavior of a nonlinear system. And as I'll show, this allows us to use linear control techniques to control a soft robot. So the Koopman operator makes this possible by representing the evolution of the state of a nonlinear dynamical system as a linear operation. So to illustrate how this works, consider some arbitrary nonlinear dynamical system. Its flow map takes an initial state and flows it forward in time according to the dynamics. Now consider some real-valued function. The Koopman operator is defined as the linear operator that composes functions like this with the flow map of the dynamical system. So if we evaluate the function at the initial state, the Koopman operator flows the value of that function forward in time along the trajectory of the underlying system. And so essentially, this lets us linearly compute the future values of functions from which we can readily infer the value of the state. Now, the caveat here is that the Koopman operator acts on functions, and this makes it infinite dimensional. So in practice, we have to settle for a finite dimensional approximation, which we can learn from data. The standard method used to compute a matrix approximation of the Koopman operator is called extended dynamic mode decomposition. And it involves evaluating a finite set of basis functions on time series data points and then using linear regression to compute the matrix operator that best describes the evolution of those functions over one time step. In this work, we improve upon this standard method by incorporating a L1 regularization term. And this term makes the resulting Koopman matrix less sensitive to outliers in the data. And it also promotes sparsity, which is important for real-time control because it improves the computational tractability. So we use this approach to model and then control the soft robot shown here. It consists of two bending sections actuated by pneumatic artificial muscles, and it projects a laser dot onto a sheet mounted below it. So first, we collected data by measuring the location of the laser dot under random control inputs. Then we used that data to approximate the Koopman operator and verify that it gave accurate predictions over time. And then lastly, we used that Koopman operator approximation to compute online predictions in a closed-loop linear model predictive controller. Shown here are several trials where, using this Koopman-based model predictive controller, the robot is able to successfully track trajectories in various shapes. And what we found is that our controller proved to be roughly 4 times more accurate and 4 times more precise than a comparison benchmark linear MPC controller. And details of that comparison can be found in the paper. Now, unfortunately, today's poster session is over, but if you'd like to learn more about this work, I'd be happy to chat about it at the reception tonight or later in the week. Thank you.